Welcome to the Explainer. Today, we're basically putting on our hard hats and taking a highly structured chronological tour of a commercial milk processing plant. Since we're diving into this for dairy industry pros, we're going to follow the product's exact path, literally from raw milk intake all the way to final equipment sanitization. We'll be looking closely at the math, the physics, and the biology that makes this whole industry function at such a massive scale. Okay, let's take a quick look at our plant map for today. We'll be moving rapidly through 6 core operational phases: raw milk and cooling, filtration and clarification, standardization and homogenization, thermal processing, specialty production, and finally cleaning in place. Let's just dive right in. Section 1, raw milk and cooling. Our journey begins the second that raw milk arrives at the receiving bay, and instantly we're thrust into a race against time and temperature. 37 degrees Celsius. Look, cows obviously don't dispense refrigerated product, right? For processors, this exit temperature is a massive red flag because it is literally the absolute perfect incubation zone for aggressive bacterial growth. If left unchecked, microorganisms will immediately trigger souring, gassiness, and proteolysis. Definitely not what we want. So, the immediate goal? We absolutely have to crash that temperature down to 4 degrees Celsius or below. We typically hit this using one of 3 main strategies: can immersion in cold water tanks, cold water sprays circulating over coiled stainless steel pipes, or just direct bulk tank refrigeration. Hitting that 4-degree mark is totally non-negotiable. It preserves the milk's quality before the real processing even begins. Moving right along to Section 2, filtration and clarification. Once safely chilled, the raw milk has to be physically stripped of extraneous materials. Now, while basic filtration just strains out the visible dirt, bacterifugation takes physical pretreatment to an entirely different level. By utilizing immense centrifugal force, we're talking spinning at 20,000 RPM, it physically rips microscopic impurities right out of the fluid. It removes almost 99% of foreign particles from the raw product. It's pretty wild when you think about it. And the underlying physics here basically just comes down to pure fluid dynamics. See, milk fat has a specific gravity of roughly 0.93, making it slightly lighter than whole milk, which sits heavier at 1.018 to 1.032. Centrifugal processing brilliantly exploits this density difference to separate the components. It's essentially raw physics applied directly to food safety. All right, Section 3, standardization and homogenization. With the milk cleaned and separated, we move to the chemical and physical adjustment phase to guarantee absolute consistency on the retail shelf. Standardization means you have to bust out the mathematical Pearson square method to precisely blend your cream or skim milk. As operators, you use this calculation to lock in the exact ratios needed to hit your target fat and solid non-fat percentages. Whether you're blending up to 5% or down to 2%, Pearson square ensures every single batch is mathematically identical. Next up, we physically stabilize the emulsion. We blast the milk through a homogenizer at a staggering 2,500 psi at 60 degrees Celsius. Why? Well, we do this to violently shatter the fat globules down to under 2 microns in diameter. This intensive physical disruption is what prevents any cream layer from separating and rising to the top of the bottle once it hits the grocery store. Section 4 is thermal processing. This is absolutely the core of the dairy plant, the critical treatments that ensure public safety by thermally shocking and destroying pathogenic microorganisms. Let's quickly compare our primary pasteurization options. Traditional LTLT, low temperature long time, requires holding milk in a vat at 63 degrees for a full 30 minutes. But modern HTST, high temperature short time, achieves the exact same pathogenic destruction in a mere 15 seconds at 72 degrees. By shifting the thermal curve, HTST is a total game changer, massively saving processing time and valuable plant floor space. But if your operational goal is UHT, or ultra-heat treatment, you bypass standard pasteurization entirely. Instead, you blast the milk at an incredible 135 to 160 degrees Celsius with 0 holding time. It's a rapid, extreme thermal shock followed by immediate cooling, giving you a commercially sterile product with incredible room temperature keeping quality. Precision is everything here, though, and things go sideways quickly when thermal parameters are missed. Overshoot your thermal curves, you yield a distinct, undesirable, cooked flavor. Underprocess it, well then you fail to thermally inactivate the native lipase enzymes. Those surviving enzymes will aggressively hydrolyze the milk fat, leading to severely rancid flavor. Section 5 brings us to specialty dairy production. Sometimes the daily operational flow shifts away from standard fluid milk processing to create specialty fermented products. Take cultured buttermilk, for example. You don't just process and package this stuff. You have to pasteurize the skim milk, cool it down to a highly precise 22 degrees, inoculate it with a 1% starter culture, and then let it incubate for up to 16 hours. Only after the coagulation naturally forms do you break the curd and cool it to 5 degrees. It is a very tightly controlled biological window. Finally, we arrive at Section 6, Cleaning in Place, or CIP. Because as any plant operator knows, processing the milk is really only half the battle. The rest of your shift is dedicated to rigorous, uncompromising sanitization. CIP is honestly an engineering marvel. It allows you to clean and sanitize miles of dairy pipes and massive holding vats by simply recirculating chemical solutions, entirely avoiding the daily nightmare of tearing down the equipment manually. It's basically the circulatory system of plant hygiene. The chemicals used in CIP really have to perform some heavy industrial lifting. They require high saponifying and emulsifying power to break down stubborn milk fats, along with strong penetrating power. And crucially, they have to do all of this while remaining completely non-toxic for food safety and non-corrosive to protect your expensive stainless steel infrastructure. The standard CIP cycle is a pretty unrelenting sequence. It kicks off with a cold water pre-rinse, then hits the system with hot acid washes at 60 to 71 degrees for up to 30 minutes just to strip out minerals. After a rinse, you pivot to hot alkali washes, like sodium hydroxide, for another 30 minutes to aggressively strip away fats and proteins. Finally, the whole shebang concludes with a sanitizing hot water rinse at up to 83 degrees. That intensive acid wash step, it's particularly vital to combat the milkstone menace. Think of it as the dairy industry's equivalent of concrete. It's a stubborn accumulation of calcium phosphate, milk protein, and hard water salts that aggressively builds up on HTST heat exchange plates. If your CIP doesn't strip this away, it completely wrecks your heat transfer efficiency and basically creates a 5-star hotel for bacteria. So, as a dairy professional, this leaves you with a critical question to end our explainer today. Your standardizations and your thermal curves might be mathematically flawless, but is your CIP protocol robust enough to protect it all? Because at the end of the day, in a commercial plant, your product is only ever as safe as your very last rinse cycle. Thanks for coming along on the tour.